Hi everyone. So today I wanted to quickly talk to you about equilibrium. So motion is simplified when acceleration is zero. Right? So here acceleration is symbolized by a lowercase a and a is equal to zero. Now we know that from Newton's second law that net force is mass times acceleration. So when acceleration is zero, net force must also be zero. Now that's not to say that there are some forces acting on the object that are non-zero, but just the net force, the total of these forces, has to be zero. Now, also, so we call this state of the object when its acceleration is zero, we call this equilibrium. Right, so just to note, we can also restate Newton's first law in terms of equilibrium. Right, so Newton's first law, an object at rest stays at rest, an object in motion stays in motion unless acted upon by a net force. Well, if acceleration is zero, we're in equilibrium. So basically we can say an object is in equilibrium unless acted upon by an outside net force. Now when it comes to equilibrium, we have two states of equilibrium, or two possible forms. The first of which is static equilibrium, and that's when an object is at rest or remains at rest, and the other is dynamic equilibrium, and that's when an object is moving at a constant velocity. Now when it comes to solving problems that deal with equilibrium, the key is going to be that our net force is going to be equal to zero. So remember, net force is the vector sum of our forces acting on the object. So our net force is, so these other forces could be normal force, gravity, friction, thrust, drag, any of these things depending on our situation. And we just have to add them all together vectorially. It's going to be very useful to us to break our vectors into x and y components. So if we do that, our equilibrium equations, in a sense, will be, as we'll see in a bit. But if we have equilibrium, basically, if we sum the forces in our x direction, they're going to sum to be zero. And if we sum the forces in our y direction, they will also sum to zero. So in physics and in math, we use shorthand if we're adding a bunch of things together in an organized way. And so we use what's called sigma notation, and basically the Greek letter sigma stands for the sum of. All right, so we are going to write a sigma in front of an F, like right here, to say the sum of the forces. And that's the same thing as saying our net force. Right, so the net force is just going to be the sum of our forces. So we can say here, if we apply this x and y component to equilibrium, we can say the sum of our forces in our x direction is going to be equal to mass times our acceleration in the x direction. And in this case, our acceleration in the x is going to be zero. And so the sum of forces in our x direction is going to be equal to zero. And we have the same thing here for our y direction. The sum of the forces in the y is mass times our acceleration in the y direction, and that's equal to zero. So in equilibrium, the sum of the x and y components of the force are zero. And I just also wanted to let you guys have some problem-solving strategy when it comes to equilibrium problems. So when you read a problem and you're trying to figure out how to solve it, we'll be practicing solving force problems a lot. But when it comes to equilibrium, the first thing you want to think about is the object in equilibrium, right? It does not have any acceleration. Right? So the two caveats of this are if the object is at rest and it stays at rest, we're going to have static equilibrium, and the object is moving at a constant velocity, then we have dynamic equilibrium. Right? We are also going to be learning about how to deal with the case in which we are not in equilibrium, so we have an acceleration. But just this lesson, we're going to focus on when acceleration is zero. All right, so now that we've determined that our object's in equilibrium, we're going to draw a free body diagram. So we're going to draw all the forces that are acting on our object. And that's going to help us solve the problem. And the AP exam often asks when in free response problems for you guys to draw a free body diagram. So make sure you draw them with a dot and not a square, because the dot is what the AP exam focuses on. So after that, after we diagram our situation, drew our free body diagram, we're going to list our knowns and unknowns, right? So we're going to determine what forces are acting on the object, label them in our free body diagram, if the certain numbers are given to us in the problem, and we need to determine what we need to solve for. What's our goal in solving the problem? Step 4 is to solve the problem, right? So what's really helpful in an equilibrium situation is that our net force is 0. So we can apply the fact that our sum of our forces in both the x and y direction is equal to 0. Oh, I apologize. I have a typo here. Here it should read with a subscript of y. I apologize for that. So now that we know that, we can use our free body diagram to identify what forces and what components are used in our sums. We'll talk about how we do that in class. And then finally, we're going to solve for the unknowns in the problem. So we're going to have a system of equations, or maybe just even one equation, and solve for our unknown we're looking for. Or solve for an unknown that'll help us solve for what we're looking for in the problem. And then finally, you should always check to see if your answer seems reasonable. So that's what I have for you guys today. So no examples in this. This is just basically concept and problem solving strategies and how to solve these types of problems. In class, we'll go through a couple examples so we can see how we can apply these strategies in class. All right, thank you guys.